So today we're joined by Verena Kain, who is joining us from CERN, and she's going to be talking to us today about AI, the particle accelerators, trends, and how CERN sees AI being taken up by the field as a whole. So when you're ready, please feel free to get started.
Okay, good afternoon, and thanks for having me. I hope I will be able to make this interesting for you. So yeah, as introduced, we're talking about AI for particle accelerators. I recently gave a very similar talk to a conference for AI for fundamental physics, and there I introduced a little bit by saying, okay, it's not so very much about discoveries with the AI that we are doing here. We know the Maxwell equations. Well, Maxwell knew them already quite some time ago, and so we know the physics. If you want, our problem is much more that we're dealing with extremely large, complex systems, yeah, you will see now how we believe that AI will help us very much with this. In particular, if we think about the next projects for high energy physics with particle accelerators. So by the way, this background here for the first slide is actually coming from the website for the machine learning applications for particle accelerators workshop. I'll come back to this. I think this was an extremely good initiative for really making AI to be picked up in the community. Okay, I start with the motivation. So why did we start this? And okay, so I'm going from CERN, so I start with CERN examples. So this is the CERN Accelerator complex. I don't know whether you've seen this before, but it's important to say that there is not just the LHC. So the LHC is the biggest ring here, the 27 kilometer circumference synchrotron, but there is a whole zoo of accelerators and transfer lines out there. And many of those are...
Sorry, Verena, let me just mute somebody in the audience.
Okay. So many of these accelerators are actually used as a chain, the so-called injector chain, to pre-accelerate the beam before it's actually injected into the LHC. And these injector machines, they are preparing the LHC beams, but next to this, they also have their own physics programs. So in these all various facilities, which you can read here, north area, east area, and so on. So these are fixed target experiments. There is LHC is a collider, but the other physics is essentially fixed target physics. And all those beams, they are being played and prepared one after the other. So every few seconds, there is another type of beam, if you want, and in this chain of accelerators, and this all has to be synchronized in the right manner. So just to say again, so there is not just LHC and LHC physics out there. There is really there are many other physics experiments ongoing in all the various facilities. And the challenge, or also in a positive sense, because it makes it interesting, is that all these different facilities, they need different beams. So we really are playing many different beam types, following different production schemes, one after the other, every few seconds, another type of beam. So this is, by the way, a screenshot from the Chamonix CERN Accelerator Performance Workshop, essentially explaining very much that there is an enormous variety of experiments going on at CERN. However, this flexibility that this injector chain has, so it really can actually, provide for so many different communities, beams, this flexibility also comes at a price. And we had in the last couple of years, we had a number of workshops where we brought together the experimental facility communities and the machines, so and the accelerator people. So there was the first one was actually in 2021. It was called the CERN Injector and Experimental Facility Workshop, and it was I think it was very much the first of its kind, at least in this sort of LHC era, and it was interesting to really get the direct feedback from the experimentalists. And what became clear is that, for example, the availability is okay. So the downtime of our accelerators. Reproducibility, however, has become a critical concern with the increasing flexibility in multi-destination operation. Now, as I mentioned, so these beams are all kind of played one after the other, and this entire chain has to be synchronized such that you extract and inject at the right moments. Now, this kind of beam schedules, they are for the time being still handmade. Yeah. So the current beam scheduling was also looked at during this workshop. This is just to give you another example, namely, has a severe impact on resources needed to run the accelerators and on efficiency. Just to give you an idea, the people actually came up with the statistics. It takes between 20 to 100 clicks to change a so-called supercycle. So this is really all the kind of what the various accelerators have to do to produce the various beams. This takes 2 to 25 minutes, and it's done 40 to 60 times a day. So you can see how dynamic things are in this accelerator complex. And then, 2022 came, and we had another type of workshop. It was then called the CERN Joint Accelerator Performance Workshop. This time, the LHC was also part of it. And it was during the energy crisis in Europe. And we were looking at all things that are actually having an impact on how much energy we consume. And we were looking at magnetic hysteresis. This picture here in the corner here, this is actually a screenshot of what is called the SPS page 1. So the SPS is the last pre-accelerator before we inject into the LHC. It's already a relatively large synchrotron, 7 kilometer circumference, and accelerates the protons to 450 GeV. Now, it has its own physics program. It has the North Area facility, relatively large facility, you can see here the various cycles that are played one after the other with the intensities that you have. Now, there is one cycle in here that is called MD1, and it is just there to reset the magnetic history from the previous cycles, essentially, such that we have reproducible cycles one after the other. Now, it turns out that hysteresis is actually a severe limitation for efficiency and flexibility in most machines, not just the SPS. SPS is a particular problem because it's already running at such a high energy. And there are these current mitigation methods, like having this MD1 cycle in there, but they are wasting energy. So just to give you an example again, so this MD1 cycle, if we do normal sort of physics, we cannot put any beam on it because it's too short. It's just there really for doing this quasi-degauss. It consumes up to about 27 megawatt hours a day. Okay, and it turns out that 15% of the yearly cost of the SPS fixed target cycle, so this is what we want to do for physics of the SPS. So 15% of this yearly cost is for waste cycles and this quasi-degauss cycle MD1. Okay, so this is one motivation that really kind of gave a big push towards I'll come back to this at a later stage to looking at how we can become much more efficient, and AI will play a big role in this. As I said, you'll hear more about this. Now, but then there is also the future. So what about future accelerators like the FCC? I'm not sure whether you heard about this, but CERN is currently working on the design of a potential future circular collider called FCC, really standing for Future Circular Collider, 100-kilometer circumference here around Geneva, going under the lake even, and so on. Now, this accelerator is much larger than the current LHC. Now, people were thinking of doing this like business as usual, FCC just like a larger LHC. So we could think of doing just a brute force scale up of the things we have been doing so far. People were actually talking about using helicopters to reduce the intervention times if you have to go to the different sites, more people, more sites, and so on. Now, luckily, this sort of route for scale up is financially excluded. Now, the alternative would be what I call here now the elegant solution, where we think about ways of building and running the FCC like we do space telescopes. This would, however, mean that we would have to reinvent entirely our exploitation paradigm, thinking of hierarchical autonomous systems, and then AI would be a key technology. Now, the good thing is it's actually the management's preferred option. I think what they're not so very much aware of yet, at least, is that if we really want to go for something like this, we need to use the next 10 years. I didn't mention this, but the FCC is planned to start with beam in the 2040s. But if you want to go for something like this, then we would need to use the next 10 years, so starting now, essentially, as a test bed to be ready with adequate design choices. So essentially taking what we have right now and really try to see how far we can push this towards being fully autonomous. Okay, so what can AI do for us or for accelerators? So the vision, essentially, in a nutshell, is it would allow for autonomous accelerators. And here the keywords are optimal control and optimization, having anomaly detection and preventive maintenance. And then, like a second order, if you want, are then differential simulations, virtual diagnostics, these sort of things. Then, of course, you would use AI for optimized accelerator design, keywords, fast executing simulations for optimization algorithms, again, very important here in this case, differentiable simulations. And then we would also, of course, use the generic AI tools for efficient research and development that are also used elsewhere in industry. Here, keywords are AI assistants for code development, knowledge retrieval, and so on. And even, I would say, conversational UIs in the control room. Okay, now coming back to this background I had at the very first slide. So, these kind of directions or the topics towards this sort of vision are also all being discussed in this workshop series for machine learning for particle accelerators that actually started in 2018. So we've had 4 of those workshops so far. The last one was actually in South Korea, in Gyeongju. The next one will be at CERN. We are already working on it. And just to show you a little bit of topics that we were discussing this year, things like, obviously, analysis and diagnostics, anomaly detection, and so on and so forth, optimization and control. I'll come back to this. But also, and I think this is important, and I will stress this much more, infrastructure and deployment workflows. We had tutorials like transformers for time series prediction, but also, again, going in the same directions, model adaptation and upkeep. Now, if you look at the general sort of trends in the accelerator ML community, you can see that the focus is shifting slowly from R&D only to AI at scale with the full lifecycle management. So I mentioned that we had this infrastructure and deployment workflows session, but it was also one of the longest sessions already, this workshop. And there were discussions about standards, so discussing standards of how we define our optimization problems, such that we can share them across labs and do benchmarking and so on. And people are starting to look at non-trivial lifecycle management questions, such as continual learning. As I said, we had a full tutorial about it. The big new theme, obviously, as every large language models. So there was the Bakuna team. So this is a large language model fine-tuned on all the papers published at our International Particle Accelerator Conference and so on. So people are looking at using LLMs for logbook search, AI assistants, and etc. So there is progress on all fronts. But I will focus now in the next slides on one particular session, namely, or one particular topic, which is optimization and control. And the reason for that is that this was really the largest session also. Now, and now within this optimization and control session, there is one topic that really was talked about the most, and this was Bayesian optimization. This was really kind of the majority of all, and people are using Bayesian optimization for everything. I don't know whether you're aware about or familiar with what Bayesian optimization is. Here's just the principle summarized. So you using a Gaussian process that you use to learn as a surrogate model, really to learn your objective function. So Gaussian processes are probabilistic models, and you use this probabilistic model to build an acquisition function where you mix essentially the mean and the uncertainty of this model, such that you can actually exploit the uncertainty of the model. And this acquisition function is the one that you actually optimize instead of the objective function directly or the surrogate of the objective function. So this acquisition function optimization process gives you your next test point, which you then apply in the simulation or on your accelerator. And then you incorporate the observed data into your model, so you condition your Gaussian process on this. So this is really a very powerful black box optimization technique, ideal for many aspects. Now, there's really impressive expertise on these optimization techniques in the community, and people have really gone beyond the vanilla Bayesian optimization. They are doing state-of-the-art BO, where people are using model-based priors for various applications, multi-fidelity, BO for laser plasma accelerators. They are using safe opt to include safety constraints and so on, many more. Now, I think one important aspect of making these kind of optimization techniques so ubiquitously used everywhere were that people were actually developing tools that made it more or less plug and play for people to use these algorithms in the control room. Now, there are several versions out of there. So at the top, you can see what Slack developed. So they have their XOpt optimization engine, and on top of this, they have their GUI, which they call Badger. And there's a similar sort of setup at CERN. Here it's called GEF, Generic Optimization Framework. It also comes with a GUI. So this is the GUIs are very much for the on-demand optimization. And they hide away all the kind of the control system complexities, which for people is really easy, and they can focus on the problem definition. Now, in addition, at CERN, we also have what is called Active for UCUB. So UCUB allows to have servers on the fly to really kind of build very easily background processes. So and with Active for UCUB, we have the way of turning on-demand optimization into background processes that can be used, to stabilize whatever sort of processes or continuous control. This was a key feature. Many people are really moving towards this. And then in addition, there is also the machine learning platform that is used to train, store, and share machine learning models with version control. Now, coming back to Bayesian optimization, I think another key ingredient was actually also coming from industry, where industry developed PyTorch. So I don't know, for people that are working with Gaussian processes, they know that they are not scaling very well with the number of dimensions and also the data size. However, PyTorch that is built on top of PyTorch with GPyTorch, Bayesian optimization can be GPU accelerated, and now this becomes much more attractive, if not even really excellent. And in addition, it allows the full kind of versatile setup like you have in Bluetooth. You can create your own acquisition functions, your own kernels, and so on and so forth. Okay, now a few examples from what people are doing with Bayesian optimization. This is an example with neural network mean priors. So given that we're dealing with Gaussian processes, people might know that including prior information through just including the historical data and conditioning the Gaussian process on it is not very efficient. What one can do is that one modifies the prior directly. So instead of a constant prior, which is the way how vanilla Bayesian optimization is implemented, one could actually use a non-constant prior to essentially use another model for your mean. Then your Gaussian process, your GP becomes a model of a model if you want. And you can get this non-constant mean from simulation, or you have it as a neural net from that which is trained on historical data, can have another Gaussian process, and so on and so forth. And you don't do this just for fun, but the reason why this is interesting is that you make your optimization even more sample efficient in this way. Okay, so now an example of what this looks like on a real machine. This is an example from Atlas. Atlas, so for those that are coming from high energy physics and are familiar with the LHC, so this is not the LHC experiment Atlas. So this is the Atlas here standing for Argon Tandem Linear Accelerator System, a machine to study low energy nuclear physics with heavy ions. And what it did here is, or the problem here was to come up with a way of having a very sample efficient optimization of transmission. So the kind of the intensity that essentially goes through the linear. Now, the problem has 5 degrees of freedom. And what they did is they trained a neural net on historical data of 3,000 data points with the previous ion species N14, and then used this neural net as their prior mean, and used it for optimizing the next run with O16. And you can see what sort of impact that had on the sample efficiency for their optimization process. So within only a few iterations, they were at almost 100% transmission. And they compared it also just kind of starting with vanilla Bayesian optimization, and it would have taken then much, much longer. So tens of iteration steps. What you can also do is you can use virtual objectives. So you can switch to what is called info-based BACS, where BACS is standing for Bayesian algorithm execution. You can have the link. You have the link here to read up more on this. The example that I'm showing here is an example for emittance tuning. Where emittance tuning is of importance for all accelerators essentially, and it's particularly important also for free electron lasers as it determines the brightness of the X-rays. Now, the classical method is to essentially minimize the emittance, is very slow, due to the fact that what you're actually doing here is a multi-point query. So multi-point query is that you cannot measure your emittance directly. You'll have to do another measurement in order to infer the emittance. So this is shown here on this plot here. So you do so-called quadrupole scans to evaluate the emittance each time. Your actual control knob, however, that you want to adjust correctly such that you have minimum emittance is the solenoid after the source. Okay. So you have here 3 different solenoid settings only, and then you, for each of those, you do these cortical scans that you do emittance. So this would be a normal way, and then you'd build your objective function, which is essentially an objective, a surrogate of your emittance, depending on your control variable, the solenoid. Now, the idea, however, of info-based maps is that you are learning another model. You were learning the model of beam size, because this is what you actually measure with the cortical scans. So you build a model of the beam size as a function of the solenoid and the quadrupole at the same time. So here you did that many measurement steps with relatively little information, and here you can see that as you scatter these measurements of the beam size, you have much more information and can therefore build much more easily a beam size model. And when you have done this, you do virtual emittance scans on the posterior samples of the Gaussian process and use this as an input to acquisition function optimization and so on and so forth. So essentially, you're learning a model, and your objective that you actually want to minimize is virtual on top of that model. And okay, so this was tried out by the people at SLAC. First of all, they did this on simulation with a noisy LCLS simulation. You can see on top of the plot that this becomes then much more sample efficient in terms of beam size evaluations that you have to do. So the blue curve is the SPAX emittance minimization. The orange one would be the normal way, where you have really emittance being your objective function. The only thing that you have to think about then here as well is, how do you know that your optimization has converged? Because if you do emittance as your objective, you can see that it has minimized, essentially has stabilized. Here, you don't have this directly, because you are learning beam size directly. So everything depends essentially on your model quality. And they use as the proxy for convergence the quality essentially directly of the model. So when the error, the uncertainty, if you want, on the model actually stabilizes, this is for them then the convergence criterion. They also tried this with the real machine. So this is a live optimization at LCLS. And they compared this actually with the hand-tuned emittance on top here, the red one. And in blue, you can see then the emittance evolution actually using BACS. And you can see that this takes a number of beam size function queries, a lot less than you normally do with their other techniques. But it is also much better than the hand-tuned one. Okay. What you can also do with Bayesian optimization, which is normally an on-demand sort of optimization tool, is you can actually turn this into continuous control by doing a couple of tricks. You can make Bayesian optimization adaptive, and then we call it ABO, adaptive Bayesian optimization. The example here is now from CERN, and it's about controlling the 50 Hertz noise on the slow extracted spill to the North Area experimental holder. If you remember, I mentioned the SPS earlier, which has this fixed target cycle in there, which all goes to the North Area. And the technique to extract this beam is so-called slow extraction, where you really create this spills of particles which are seconds long. Now, this for the experiments is very important that there are the flux is essentially constant. So really the intensity per time unit stays constant over this 4.5 seconds. However, we have the 50 Hertz noise from the power supplies from the European grid, and this creates intensity fluctuations at 50 Hertz. To correct those, we can modulate the voltage of our main quadrupoles at n times 50 hertz. The only issue is that the spill noise changes over time following the European grid also. Now, to be able to follow, we'll have to become adaptive, and you can do this actually also with Bayesian optimization. The trick to do here is that you do not just learn the objective function as a function of your control variables, x, which would be phase and amplitude in our case, but you learn it as a function of these control variables and time. And okay, then you use special kernels for the time dimensions. This is maybe not so important here, but what you then do is that you essentially forecast. So use your model then, and you forecast one time step into the future, and you optimize at this one time step into the future to find the next best phase and amplitude for correcting this spill noise. And you can see here plot what this looks like. So this kind of tracks as a function of time, and the dashed line is the limit, and it has to stay below this 0.15 normalized amplitude here at 50 hertz. And this is then an overall comparison. So we were trying various techniques over the years. This is for 100 hertz, so an harmonic of the 50 hertz. So before we essentially used ABO, we could not get to what the experiments want from us, that we stay below 0.15 in normalized amplitude for at least 85% of the spills of the shots to the north area. So we have to be here in this corner here, and now with ABO we can do this. And this is, by the way, extremely important for the future experiments that are planned in the north area. There's, for example, SHIP. I don't know whether you heard about this, an experiment for the search of hidden particles. Okay, now another topic that has become very important also are differentiable simulation codes. You probably all know that optimization algorithms work best and are most sample efficient with the gradient information of the objective function. That's the reason why people are also investing now on the accelerator side in so differentiable codes. An example here from our DAISY colleagues is Cheetah. It's a high-speed differentiable beam dynamic simulation for various machine learning applications. So they have come up with this, and okay, they are using this for doing gradient-based tuning directly at the machine. So they just get the gradient information from the simulation, and then use this in their optimization algorithm to optimize online. But you can also do what we were talking about earlier. So you can actually use the simulation as it is differentiable directly as your non-constant prior mean, as we were discussing in a couple of slides ago. It needs to be differentiable because as part of the acquisition in the acquisition function, this needs to be very efficient. You need to be able to optimize this in a very efficient manner. But in addition, it does not need any data to train up because it's a simulation already. You do not have to go like earlier to build the circuit models from historical data. You have the simulation there. And then you can do, of course, very sample efficient Bayesian optimization using these gradient informations, or you can do something like this. So this is a very neat idea that, by colleagues from SLAC here again, so the Ryan and team. They use differentiable simulations, so beam simulations, to do generative phase space reconstruction. Okay, the original version was for 4D, now they have extended it to 60. This really kind of combines all sorts of aspects, generative AI together with differentiable simulation. So normally to reconstruct the 60 phase space, these measurements are rarely done because they're extremely time consuming. So there is just an example from the spallation neutron source from SNS. for them to do something like this, it took them 5 million measurements, and this took 36 hours to collect all this data. Now, Ryan proposes something like this, or Ryan and team, they propose this. So you start with having a generative AI model that generates a initial particle distribution that you feed through your differentiable accelerator simulation, and it generates, with some quadrupole settings or whatever, some sort of images in simulation on a given screen. You also take these measurements with the same settings from the real machine, and then you compare this, you build a loss function, and then you back propagate all of this to update the weights of your net that you use to generate your initial particle distribution. And in this way, they could actually take only 20 measurements, as you can see here depicted, to do a full 60 phase space reconstruction. I think it's quite impressive and actually quite promising, actually, to see how we can use this type of techniques for many other things. Okay, now reinforcement learning. So Bayesian optimization, we talked about it a lot. Differentiable simulation is important now, but where is reinforcement learning in all of this? Now, there was DeepMind's paper some time ago. I'm sure you've seen this, where they came up with a way of using RL to do the magnetic control of a tokamak plasma, which is a very hard problem, time-varying, nonlinear, multivariate. Okay, and they trained this control policy with 92 inputs, 132 targets, and having 19 actors, or the outputs essentially. So they trained this control policy on a simulator, and then transferred to real, and actually really managed to control the plasma in the shapes they wanted. So this is exactly our setup, accelerators as well. Now, why have we not talked yet about RL in the talk so far? Now, reinforcement learning, just to introduce this very superficially here. So the difference to doing optimization, or even online optimization, or even continuous control with ABO and these sort of things, is the reinforcement learning brings in one more abstraction, is that it actually learns the dynamics and therefore is more generic, if you want, for a given setup, for a given problem. So it does this hopefully once and for all through trial and error, and then does not need, in principle, any exploration afterwards. So you've probably seen these sort of schematics. This is here an RL setup for learning how to do trajectory steering. You have an environment where you can set corrector magnets. So you get your BPM readings as observation, which are transformed to a state as input to your RL agent, and the RL agent then comes up with the corrector settings as the so-called actions. Now, for tuning this policy, the environment feeds back the reward, and the objective of this RL agent is to maximize the cumulative reward. So this is how it works. Elegant, actually, if not ideal. However, online training, so directly training on the machine, is often not possible. These algorithms are still not sample efficient enough. And in addition, we have safety constraints sometimes where you would not want to have an untrained agent on the machine and causing beam loss and these sort of things. Still, if there is one more other aspect, is that if you want to go to something like reinforcement learning and also actually model predictive control, you need to build this into the accelerator design. So the reason why we don't have RL as much as we should, I don't know, is not necessarily only that they are not sample efficient enough, but it's really that our accelerators were not built for them as we have them now. But they are so promising and for so many aspects that the next generation accelerators needs to be built for RL. So what that means is that we have to have fast executing and accurate simulations or digital twins for training. So what we've really gone away almost entirely for training from training online. We train on simulators and then transfer to real. And then we also have to have the instrumentation designed with the control algorithm. And this is actually also a very important part that is missing very often. Okay. Now, just to make this point clearer of what I mean, so why can't we just use RL easily? I'll give you an example again from the 50 Hertz controller at the CERN SPS, where we actually tried to first solve this with RL. And this is already some time ago. As you can see here from the title, we didn't actually go for this in the end. So we actually were doing this with a simulated environment, sort of a really simple setup where we're looking at a 1 second chip cycle, 2 kilohertz spill monitor signal, and then trying to really kind of correct the ripple. And very simple. If you knew all the constituents, you could measure all the constituents. You can do this analytically. We don't have this, so that's why we have to come up with something else. Now, it turns out that you can actually train an algorithm, RL algorithm, on this. Sorry for this plot. So this is really from this relatively old slides, which are just copied over. So you can see here that the reward is kind of stabilizes. It kind of always makes it after some training period to where it should be, beyond threshold. And also within a relatively few steps each time. So this is done with the algorithms T3 and SEC. Okay, there you could choose others. So this would work in principle, but you can see here the number of episodes, and this is not the number of iterations. You still have to multiply this with the iterations here. So this would have taken tens of thousands of iterations on the machine. So you would think, my goodness, this takes long. Can we just transfer with what we have here? Now, okay, not so easy to translate with that particular simulation from this correction setting that we have to the voltage setting that we really actually apply. Okay, one could probably figure this out somehow and to see how we can actually really match all of these things. So we would really need really good digital twins and so on, which we don't have. Then, okay, if you say, okay, it takes long, the training, but it's not that long if you have to only do it once, like once for several years, because in principle, there's maybe no reason for this to change ever again. So we could maybe think of having a commissioning session, like, a day or a night to just run this and train this. The other problem is, however, if you want to do this and train this online, is we do not actually have any way to change the spill noise, the underlying spill noise. Really, this is the European grid doing this for us. But for being able to train this for each episode, we essentially have to give it a new kind of problem to solve. Okay. Also not straightforward. If we built this entire thing in another way, you could probably see that you can inject another sort of noise source that is just there to disturb the entire system, which you wouldn't have to correct with the quadruple modulation that we inject. Okay, so, but there is a RL at CERN. This is just a selection. So we're using reinforcement learning to correct the RF phase and voltage for uniform bunch splitting in the PS accelerator. So this is needed for the LHC beams. In the PS to SPS transfer, we have the injection kicker. We adjust the fine delays for those with RL, and actually it's also a partially observable system, so relatively non-trivial. This was trained entirely on simulation. For Linux 3 and Lear, so this is now the ion, so the LHC can run with protons and heavier ions. And then the first machines in the chain are Linux 3 and Lear. Here, to optimize the injection efficiency, there is a reinforcement learning agent is being trained using a state based on a variational autoencoder encoded Schottky spectrum. Again, agent is trained on a data-driven dynamics model, not on the real machine. And the final example here, that's again for the SPS, the transfer line between the SPS and these north area targets. So this low extracted spill is essentially DC beam. So you can't use the normal beam position monitor techniques. What they use instead is they essentially measure, instead of position directly, they measure intensity on different foils. So the normal sort of beam position or trajectory correction algorithms, they fail with those to some extent, but RL doesn't have any issue with it. You can train for that. We trained in simulation and transferred to real, and that was also working. We did this during the commission. And then there is the RL for AA workshop series. This is reinforcement learning for autonomous accelerators, where there is now a little community building up that is really pushing the frontiers of reinforcement learning for accelerators. The last one was in Salzburg in Austria, and it's nice to see that that there is there's this, first of all, the community forming, but that with the input from industry and so on, that we kind of really all pulling in the same direction. And there are, you know, like the kind of reviews from the various facilities using RL, but then we're also working on advanced RL concepts. So this was really part of this workshop also. So questions that are important for us to answer are, so if we go for RL and if we kind of figure all these things out, how are we dealing with time-varying systems and partially observable systems? Because this is what we have very often. There are different answers to this, and what we looked at this time was meta-RL with the algorithm MAML, so model agnostic meta-learning. You can see a little bit here the what this algorithm does, but in principle, it is that you learn to learn. You actually need a simulator. So this does not work without having a very good simulation. But in the simulation, you do not just learn one task, but you learn several tasks. And the policy the meta policy that you end up with in the end is such that it will learn the real task that it has to solve on a real machine very quickly. So this is the idea. We also tried this actually with a real machine. This it was tested with the awake electron line with trajectory steering. So awake is a facility at CERN where they're doing tests for plasma wake field acceleration using the proton beams to create the wake field and for the electrons. This is really our kind of MNIST data set, if you want, is our MNIST sort of test facility. A lot of algorithm development was actually done on this line, just because it has a very high repetition rate, and also if you lose the electrons on the vacuum chamber, you do not shoot a hole. So we tested this meta-RL algorithm, the MAML, on this setup. You can see here the comparison with various different algorithms, off policy, on policy, and so on and so forth. And you can see that if you go for this meta-learning approach, then you are extremely sample efficient. It will know very quickly of what to do in the real setup. Now, this is to some extent a little bit misleading, because some of these algorithms you really can use to train online. So these ones, for example, you can actually switch them. You can train this particular problem, no problem with this number of iterations needed. You can actually do the training online. Also, if you go model-based RL, you do not need any good simulation. Here, the number of iterations that you do in simulation are, of course, not counted, really only on the machine. Okay, now, so I was talking a lot about different, what people are working on, what particular trends we have now. Now, to answer a little bit the question of where the whole thing will be going, one really important next step, I believe, is that we have create a splash. So we need big strategic and ambitious project to use AI at scale. And I think this project here, this is probably one of them. So this is a project about maximizing proton polarization at RIC, at BNL on Long Island, in New York. And this is really the preparation towards the next collider they're building there, the EIC. This is really consisting of numerous sub-projects, from improved modeling to fast and slow control and optimization. And they're working on various areas to optimize. Booster injection and captures is one of the machines there. The HES is another accelerator. HES sponge splitting and merging schemes, and then the HES spin resonance compensation. And just to give you this once screenshot of one of the slides here concerning the HES sponge splitting and merging, where they are proposing to use this with reinforcement learning. And then I'm mentioning this because this is very similar to what is happening already at the PS with the bunch splitting optimization for the LHC beams solved with reinforcement learning. So they are actually working together on this to profit from the synergies already. Now, another hopefully big enough project is the Efficient Particle Accelerators project at CERN, which is all about automating accelerator exploitation. So this was approved last year in autumn after this pre-study in what was called then the efficiency think tank. And it was essentially really triggered by what I was mentioning in the first couple of slides. So these inefficiencies that were highlighted in these couple of workshops that we had in 2021 and 2022. Now it consists of 9 work packages, very much following the ETT recommendations and also some control infrastructure evolution. But here we're talking about, I was mentioning it earlier, the dynamic beam scheduling that should be fully automatic, the hysteresis compensation, and so on and so forth. Now, okay, I was mentioning hysteresis compensation but was not talking about it very much at all anymore, because it's not directly optimization or control, even though it's going to be solved hopefully with AI enhanced feed-forward control. Just to give you one update on what one of our PhD students is doing here. So we are building a data-driven model of the hysteresis effects and the eddy current decay to forecast the magnetic field for the next cycles to be played. So this is the idea. So we forecast this as a function of the fields from the past and the currents of the past and for the next cycle. Okay, so this is now being piloted on the SPS main dipoles. This is really kind of, this type of hysteresis effects that we can see here. So you end up on these different loops because we are using the magnets deep enough into saturation. We have, with hysteresis, we have these issues everywhere, also seeing it actually on slow extraction. So in slow extraction, what you want to do is you want to keep this shaving of the beam in the machine. This is kind of the beam in the machine as it is measured as a function of time. You want this to be really kind of linear, such that you have the extracted rate constant to the north area. Now, if you have these field changes due to the cycles that are being played before, you get these sort of variations, and then also the spill shape will change, and we measure this sort of through the so-called spill duty factor. It should be close to 100%. for optimum spill quality, kind of having really constant spill. And if it goes away from this, then you're not so constant anymore. But just to show you, so the where we are now with this, after the first data collection series and building the first models, okay, this is the various models were tried via LSTMs, but also transformer-based models. We can actually already stabilize the effects from the main dipoles. We don't see them so much then anymore on the slow extraction, for example. Here's a super cycle change. So this, at the beginning, you're playing cycles with the LHC beam in there. Then you remove the LHC beam. You only play fixed target beams and this MD1 beam as well. You have this sort of spill duty factor. The green shaded areas is when you have the compensation on. Okay, it does not deteriorate the spill duty factor. This is already one thing. Then you change the super cycle. You put the LHC cycle back in. This significantly reduces the spill duty factor. Then you switch the compensation back on. Based on this transformer here, and it actually recuperates the spill duty factor. So this was already very good to see, and this work will continue for the rest of the complex. Now, okay, so the efficient particle accelerators project at CERN here has 5 years to implement, all these efficiency improvements everywhere, such that things are ready for what is to come next at CERN, which is the HL-LHC, so high luminosity LHC. So at the end of 2025, LHC will end, and then we'll stop the machines for about 3 years and upgrade the LHC. And then we start back with HL-LHC. And when we come back, the improvements from EPA should be in place. Now, this is really for the near future, but at the same time, I believe also that EPA is preparing a new CERN accelerator exploitation paradigm. I don't think it's going far enough to really look at all the aspects that are needed for something like the FCC, but at least it's blazing the trail towards it. Okay, so this brings me to the last slide with hopefully the main takeaways. Now, AI is changing also how we exploit particle accelerators, and it will enable many more new possibilities. Now we have to just embrace those, which is also not given always. Now, I think what was very important for our community is that the people who came up with this machine learning workshop series, this created a global community for ML for particle accelerators, and it really cross-fertilized and inspired labs. So what's the status? I think we're using state-of-the-art AI in R&D and small-scale operation installations. What should be next, and this is not there yet, will hopefully come, is that we are doing AI at scale. And this means also tackling infrastructure questions. So we'll have to move from things are working once to things are working always. And this, I believe, can only come with strategic, ambitious sort of moonshot projects. And hopefully there are some now. That's it. Thank you.
Thanks very much. Yeah, thanks very much for that really comprehensive talk covering lots of different aspects of CERN and accelerator physics. So what we'll do is, if people online have got any questions, please raise your hand or drop them in the chat. To start with, I'll take any questions in the room. Okay, David.
I hope you can hear me. One thing I was going to ask was, a lot of this seems to be sort of building the digital twins. So it's having the simulation at a good enough state that you don't have to run the AI directly on the hardware. How much is the improvement going to be in the actual AI models, and how much is it going to be in making good digital twins?
So, very good question. I think digital twins or kind of having really good simulations is going to be a key for whatever we're going to do next. However, what we see also is for machines the size of the FCC, you cannot even simulate those anymore easily, at least. if you take all the effects that there are, all the collective effects in there as well. So the one step towards all of this is that we have fast executing simulations. And this comes again with AI. So we'll have to improve even the simulations using AI. Okay, you could think of surrogates or having this mix of some of the processes are AI models rather than the actual simulation. But then you can actually easily integrate this with the rest of the simulation. So this is also going to be extremely important.
Okay, thanks. No, it's just that you were talking about, I think cheater it was, where you got as soon as you've got a differentiable model, you don't really need AI. You just sort of minimize it to wherever you need it. So it sounds like that's the hard bit, and the sort of. But I can understand that if your model is so enormous that you can't calculate it, then you need other ways of doing the simulation.
Yes, exactly. So the differentiability is one aspect. So if you have a surrogate model of your simulation that you trained on simulation and you make it foundation enough such that you don't easily get out of the main, you are automatically differentiable. So differentiability is one thing, but the other thing is really speed. And okay, if your simulation is differentiable but not fast executing enough, it still doesn't help you in the control room. Yeah.
Thanks.
Okay, so one from me. So what we're trying to do here is look at all these different fields that are exploring different aspects of data science, machine learning, AI, all this kind of stuff. So I was wondering, are there any other fields that you personally are kind of looking at for inspiration, or CERN in general? And I know you mentioned telescopes at the start. There's some quite big ones coming online in the same kind of timescale as FCC, say like square kilometer array and other things like that. Yeah, are those an inspiration in terms of the techniques they're using?
Yes, so just rather recently there are all these common workshops for fundamental physics and AI and so on, and this is always you have nuclear physics, you have cosmology, you have you have of course high energy physics and so on. So in terms of physics, I think we are definitely getting very much inspired by what other people are doing, and specifically also in the high energy physics community, what the detector people are doing. So they have been doing AI for much longer than we've been doing it. They have maybe to some extent different use cases, but I think it is important nevertheless to use those things that we share and have in common. I think it's less the case with biology and these sort of things. Yeah, we simply don't have that much contact with other fields.
Interesting. Okay. Any other questions in the room? No, if not, one final from me, because I suspect we might be kicked out of our physical room in a second. Is there any feeling that these kind of techniques that you want to be bringing in for HL and for FCC, are they going to be required for any new science, like any kind of breakthroughs in the standard model? Like, are these an essential component, or is it more, yes, we can achieve the performance we want without these models, but it becomes kind of tricky? If we can do them, why shouldn't we?
So, okay, I think FCC without AI, forget it. HLHC we can discuss, obviously on the accelerator side. I believe on the accelerator side, we can continue running the LHC the way we're running it right now. Essentially, HLHC will not be fundamentally different to the LHC, and the LHC works fine, you could say. For me, deploying these sort of things is in terms of LHC and so on will be much more important as preparation for what's coming next. Now, if you also want to do a global optimization of what we're doing at CERN, yeah, be it energy consumption, be it kind of increasing the flexibility further, increasing the reproducibility, also for people like our stepchildren, the fixed target facilities, yeah, then I think we'll have to invest into AI. We will not be able to do it otherwise. It needs really automation.
Okay. Okay, thanks very much. So I think we can finish it there. So let's thank our speaker one last time. So that's it for the 2023-2024 academic year in terms of this data seminar series. However, if you've enjoyed these talks in general and you want to kind of come to Liverpool in person, next month we're hosting STFC Data Science Summer School. We have like a week-long program with workshops, lectures on topics across physics and data science and AI more broadly. So if anybody online is a PhD student and would be interested in attending that, particularly if they're funded by STFC, in which case it'll be free for you, then check out our channels and I hope to see you in Liverpool next month. So apart from that, we'll see you in September, October, I guess. Thanks again, Verena.
Bye.
Bye.